All right, friends, welcome back to this lecture, Chemistry 132b, and we are going to continue our discussion of the extra problems that were posted online, and try to kind of give the answers, but also give maybe a little bit of feedback on how to solve such problems. So I'm going to dive in right away, unless there are some questions from you guys. Just let me know if there's anything else I can help you with at this point. I'll be glad to do that. All right. Seems like everybody is happy at this point. Okay, so I'm going to start with problem 5. That's the we basically went through problems 1 to 4 last time on Monday. So problem 5 is next. And it is a problem about a particle on a ring, as you can see. You see a picture here. And there is also a wiggling thing shown. That is, of course, my wave function that is shown. It says here, consider the real part of the wave function for an electron on a ring as shown above. The radius is also given. It's 1 angstrom. So this is the real part of the wave function, because probably, as you know, the wave functions for particles on a ring have a specific shape or expression. So we can write it as a wave function, as a function of theta, and also has a quantum number, ml. And these functions all look like this. So this is a normalization factor. R0 is the radius of the ring, which in this case is 1 angstrom. And then the function itself is I plus minus, well, let's do it. Well, that's okay. That's all right. Can I erase it? No. We go like this. This is better. Sorry, folks. I don't have an eraser on this thing. Okay, there we go again. 2 pi r0, and then exponent plus minus I ml phi. Okay, so those are the general expressions for the particle on a ring, wave functions. This is a complex exponential, so it has a real part and an imaginary part. An imaginary part we can draw, but here it is shown for the real part. So this is a wiggling function. Probably you know that the complex exponent has a real part that looks like a cosine, and the imaginary part looks like a sine wave. Okay, so this is the cosine wave, and it goes around the circle. As you can see, wherever it starts, let's say it starts here, okay, then it goes around the circle and comes back to the same point, and it is continuous, right? That is a requirement that we want for these wave functions. Okay, so this is the situation. It says, give an expression for the normalized wave functions shown in the figure. We already completed that, almost, because there's one more thing that we can fill out here, and that's going to be important as we move along with this question. We can actually count how many swings this wave function makes if it goes around the ring. Okay, so I can start with this one here. Well, let's start over here. Let's take this as a starting point. We can take any point as a starting point because it's a ring. There is no beginning or end. But let's say I start at the arrow. I can say this is the first one going up. This is the first one going down, this one. This is the second one going up right here. This is the second one going down. So there's like 1, 2 swings so far. This is 3. This is 4. And this is 5. Okay, so there's 5 swings, full swings around the ring. 5 full cosine swings around the ring. And that means that this ml is going to be 5, right? So the wave function, therefore, looks like this. It's the same one, but now I can fill out a value for ml. ml is plus or minus 5, okay? So 5 I phi, something like that. That could be the correct answer here. Why is it plus minus? Why can't I say it's plus? We go one way, right? But that's, of course, arbitrary because I could have gone the other way. Okay, so I have no information about the angular momentum of this particle, other than that it has a value 5 that could be either plus or minus. Okay, so this is the answer to question A. Question B, compute the angular momentum of the particle. Okay, so how do we do that? Well, we know that we have to do something like this. This is the operator for angular momentum of the particle. This is the projection along the z-axis. That's the only projection I can make for this particle because it only moves in one dimension. So Lz is the relevant operator here. I can operate on this wave function, and what I should be getting is some sort of an eigenvalue, which in this case is going to be ml h bar and then times the eigenfunction again. Okay, so what I'm looking for is the value of this eigenvalue. That is the angular momentum of the particle. Well, it's not too hard to figure that out because ml we just determined. Okay, ml was plus or minus 5, and that means that the answer here is going to be the angular momentum of this particle on the ring is going to be plus or minus 5 h bar. Okay, so that is the angular momentum projection onto the z-axis. That is the only angular momentum I can compute here. There's no Ly or Lx in this case. All right, so what is the energy associated with this motion? So here I'm being asked to calculate the energy. The energy is given, and this is an expression that will be given on the sheet that's provided on the exam. There's going to be a sheet with constants and expressions, and this particular formula will be part of that. You can also just maybe memorize it. You don't have to, but people who have done this many times will know that this is a general expression for the energy of a particle on a ring. So ml squared, h bar squared, then 2 times I, where I is going to be the moment of inertia, right? So what do we have? We can actually fill out some of this. So ml is plus or minus 5. So a square of that is 25. 25 h bar squared. And then I have 2 times the mass of the electron times r naught. And r naught I also know, because that is 1 angstrom. So in principle, I can calculate the energy in terms of an actual number, because I know what the constant of Planck is, h bar squared. I can compute that. H bar will be provided on the exam in the table of constants. Me is also part of that table, and r naught is given. So I have all these values. So I can just come up with a numerical value for this energy. And what I find, if I punch in all the numbers, is 1.52 times 10 to the minus 17 joule. Okay, so that's what this particular calculation gives me. Oh, actually, there should be a square here. Sorry. Me times r squared. Okay, the next one, that's a good one. Based on the probability distribution for the electron, identify the number of nodes along the ring. This is a kind of a little bit of a stinker, I think, because if you look at this picture, you say, oh, look, it has 1, 2, 3. Basically, you're going to count all these 0 crossings here. But this is actually the wave function, as you can see here, the real part of the wave function. So it's not the whole thing. Okay, you cannot just look at this picture and assume that the real part of the wave function represents the entire wave function. That is not true. Also, the probability is given by the modulus square of the entire wave function, right? So in general, I can write the probability P between, let's say, 2 points on the ring, let's say between point A and point B, is going to be the wave function itself, the modulus square of the wave function, and then r naught d phi. Okay, that is going to be the probability of finding the particle on the ring between points A and B. Now the density, probability density, is just this whole argument here that you integrate over, right? So I can say, what is the likelihood of finding the particle in a very small volume element, very small element along the ring, that is going to be the probability density. That is the same expression here, R naught d phi. Okay, so this is going to be really stocky. Very sticky. I don't know. It doesn't. My mouse is a little sticky. So this is the general expression for the probability density, and it's a probability of finding the particle in a very small element along the ring, d phi. Okay, so very small element along the ring, d phi. This is the probability of finding the electron. So what is that probability to find the particle at any position here along the ring? Well, that is just the square of the wave function. So what am I getting? Well, if you do the square modulus of this whole thing, this complex exponential square modulus is going to give me 1. And then this prefactor here will give me 1 over 2 pi r0. Okay, and then times r0 d phi. That is going to be r0 is going to be 1 over 2 pi d phi, right? So what does that mean? There is a chance of 1 over 2 pi to find a particle anywhere along a particular element along the ring, d phi. So that's the same. For each particular position, d phi, any little very, very small element here along the ring, d phi, has an equal chance, namely 1 over 2 pi, of finding the particle. So that means that there is no particular place where the particle has a lower or higher chance. It's the same along the ring. There's an equal chance of finding the particle anywhere along the ring, and this chance does not depend on position and does never go to 0. It's constant everywhere. So there is no knot. There is no node. Sorry, not a knot. There is no node on this ring anywhere, right? So the answer here is that there are no nodes. There are no nodes here. No nodes. So it's a little bit of a trick question, looks like, but this is actually a very important realization for the particle on the ring. The modulus square of the wave function is constant everywhere, which means there's an equal chance of finding the particle anywhere along the ring. And that is an important physical thing to remember about the particle on the ring. Okay. Anybody? Any questions about this question? Okay, let's move to the problem number 6. Very different problem. It says that sodium has 11 electrons. Okay, I believe that. And then consider only valence electrons. That's good, because that means I can forget about the first 10 electrons. They're all core electrons, and the only electron left, the only valence electron, is all by itself, which means I only have 1 electron to worry about. First question is, what is the term symbol of the ground state? Okay, the term symbol of the ground state for this particular electron. Remember, I'm forgetting about all the other electrons. So it is going to be in the S state, right? So that is going to be important for me. So I'm going to write down for the single electron, I have S equals half. And this electron is in the S state, S orbital, which means L equals 0. Okay, so that means that I can make combinations of S and L to find the total momentum of the particle. But since L is 0, there's only one possibility, right? So the term symbol, therefore, equals a value S, because L equals 0. There's only one electron. That means an S symbol, because that stands for total orbital angular momentum being 0. Then the multiplicity, which goes up here, is going to be 2s plus 1. This one, 2s plus 1. That's going to be 2. right? And then the J value that's going to be here below is going to be the combination of these two guys. But since L equals 0, there's only one combination, and that's half. So what I'm finding is S with the multiplicity 2, and then 1/2 for the total angular momentum. This is called a doublet. It's a doublet state for a single electron. Okay, that's it. That's question number A, or question letter A. Then question B, sodium can be excited to this particular state, neon, and then 4d1. So this is an excited state of sodium. So this single electron now is leaving the s orbital and is going to a d orbital, right? What are the term symbols now? So again, I have one electron, so s is still 1/2. It's only one electron to worry about. L is now in a d state, which means it is 2. Okay, so it's now no longer in an s state, it's in a 2 state. But you can see it was previously 0, now it's 2. So this transition is more than delta L equals plus or minus 1. So this particular transition cannot have been mediated by a photon, but could have been mediated by a different process, for instance, putting heat in the atom. Okay, so that's just a detail, just to let you know. Not every excitation needs to happen through a photon, for which there are strict selection rules. We can also excite the electron through different means, putting energy into the system through different means. Okay, so these are my S and L, and what I have to figure out now is the term symbol. So the letter is determined by the L, the total orbital angular momentum, has 2, which means it's going to be a D symbol. The multiplicity is 2 again, all right? And now the J value can have 2 different values because it can be 2 plus half and 2 minus half. Those are the only 2 combinations I can make. They're separated by 1 integer step, and that's it. So I only have 2 values, which is 5/2. That's the first combination, and then D of 3/2. That's the second one. So this is, of course, 2 plus half, and this is 2 minus half. 5/2 and 3/2 are the 2 solutions for J. So just a few words about this. What is the right way to think about this? So let's look at this situation here. I'm having a single electron, and there are 5 d states, right? So here we are. There's 5 d states. There's a single electron. Single electron can be either spin up or spin down, and it can have 5 positions, 5 particular orbitals in which it can sit. So if you ask me what is the total number of states that the electron can be in, that is going to be 5 positions, 2 spin states. So 5 times 2 equals 10. There's 10 possible arrangements of this single electron, right? Hope you agree with that. So what happens after spin-orbit coupling when I'm considering that there's an orbital source of angular momentum as well as a spin source of angular momentum, and they can combine either positively or negatively, right? So I get a case where the spin and orbital combine in a plus way and in a negative way, and therefore I get 2 term symbols. Now the first term symbol, D 5/2, has this value here for J. The total number of states within this term symbol is given by 2J plus 1, and that equals 5 plus 1 equals 6. There's 6 possible states. Okay, so the electron can be in this term symbol, and there's 6 possible arrangements in which the electron can be in that term symbol. Second one is D 3/2, and that's going to be 2J plus 1, same way, but now I get 4. Okay, so there's 4 possible states in which the electron can sit in this term symbol, and that means I have 10 possible states. I have 10 possible ways to put the electrons in this configuration for D1, right? So the number of states hasn't changed, same before and after spin-orbit coupling. The only thing that spin-orbit coupling does it says, okay, there's 6 ways in which I can make a total angular momentum that is 5/2, and there's 4 ways in which I can make a total angular momentum that is 3/2. Right? And so that's what the spin-orbit coupling does. It splits these possible states. Previously, they were all the same, degenerate, and now they're going to be non-degenerate. Okay, question C. The orange glow of older streetlights is due to the emission of an electron that occupies 3p1 in sodium, and it falls back to a lower lying state. What are the term symbols for this possible final state? That's one question. And then, how many lines do you expect? Okay, so what's going on here? Initially, it's in this 3p1 state. And so let me quickly figure out the term symbols for that first. I have L equals 1, S equals half. Okay, so the total angular momentum, orbital angular momentum is determined by L. So it's going to give me a P symbol. Then I have multiplicity is 2 half plus 1, that's 2. And then J can be either the plus combination or the negative combination of these 2 values. So I have 3/2. It's the first example, the first possibility. And the second possibility is 1/2. So J is either 3/2 or 1/2. So these are the 2 states in which the electron can sit when it sits in this particular configuration, 3p1. Falls back to a lower lying state. The only state it can fall back to is actually the S state, where we started from. Okay, the S state where we started from is this state. Okay, so that is the ground state of sodium. This is the excited state. And so what I can do now, I can fall back either from this level to that level, or from this level to this level. So from the excited state, P 3/2 back to S 1/2, or from P 1/2 back to the ground state S 1/2. So there's 2 possible ways in which this can happen. And therefore, there's 2 lines. There's 2 lines that you may observe in your spectrum. That's one of the reasons why it's called a doublet. Okay, so the ground state is this term symbol, which we had already answered in question A. And then in question C, we determined these 2 excited states, and that gives us 2 possible ways we can make a transition. They are allowed because the delta L equals 1. From a P to an S, delta L equals plus or minus 1, and that those are allowed transitions through the emission of a photon. This energy, in fact, you can compute for these 2 lines, and indeed that gives you an orange type of radiation, something like 580 or 585, which is orange, and that is that explains the orange glow of the streetlights that people used back in the day. We don't have them anymore; it's all LEDs nowadays. But back in the day, most streetlights were actually sodium lights, sodium lamps. Okay. Any questions about this? Make sure you know how to determine term symbols. It can be confusing sometimes, but just do it a few times, really. And once you get the hang of it, it's pretty straightforward. Okay, problem 7. This is about the hydrogen atom. System is in the ground state, it says. Okay, perfect. And then the first question, A, says, calculate the most probable radius of the electron. Ooh, okay, so now I actually have to calculate something. This is the first time I really have to do maybe a little bit of math. So how do I do this? Well, I have to know what the wave function looks like when the electron sits in the ground state for hydrogen. So I have to look at the table. Unfortunately, those tables are given on the exam. Again, you don't need any information really to do the exam. All the information is provided. All the formulas you need are in principle provided on the exam. So this is one of the tables that's provided, and this is the table that we would need. We have a hydrogen electron. That means it sits in the ground state, 1s state. So n equals 1, L equals 0. So this is the radial wave function that I need. That's the one. Okay, and then I need to determine the most probable radius of this guy. So R, n is 1, L is 0, okay, as a function of R. Let's write this out in terms of R, because this is given in terms of rho, and it has, you know, it depends on R, but there's a prefactor. So let's write that out, and also realizing that Z equals 1, just to clean up this expression a little bit. I have this one here, and what I'm finding is minus R over A. Okay, because if I fill out this divided by 2, that gets rid of this 2 over here. Z is 1, n is 1, so it's 1 over R with a negative sign. This is the expression that I'm getting. Now, what is the radial distribution function? The radial distribution function PR equals R squared times this wave function, the radial part of the wave function, squared. Okay, so that is what I have to compute. And so what I'm getting then is square this whole thing. So I get 4, square this thing. I get the argument now to the power 3. And then R squared, that comes from this guy here. And then this squared as well. So 2R over A. Okay, so that is the radial distribution function. How do I find the most probable radius? Well, I have to take the derivative of this thing and then find the roots, zeros of the expression that follows. So what I have to do, I have to realize, of course, there's 2 functions here that depend on R squared, and this exponential. So I have to use the product rule if I compute the derivative. Okay. So I can do that, of course. So first the prefactor that I can take out just to clean it up a little bit. And then I'm going to first take the derivative of this guy and then times this complex exponent. That's one term. The second term is R squared and then the derivative of the complex exponent. Okay. And so what I'm getting then is 2R, the first one, and then minus, this is going to be the second one, R over A, and then minus R, this one. Okay, so this is what I'm getting. This is the first derivative from the product rule, 2R times the complex exponent. The second part is 2R times R, okay, because I've made a derivative here. So the derivative is going to be minus 2A, that's this one. I can take a 2R out, so this is where the negative sign comes from, and the remaining term is R over A. So first part of the product rule, second part of the product rule, and then taking the 2R out of this sum, so I can clean this up a little bit. I clean this up a little bit in this way because it's easier to see where the root will be, the roots of this equation, because this is going to be 0 to find the maximum. Okay, so this is the derivative, of course, of the function PR. I set the derivative to 0, I can find the maxima, and I see 3 possibilities. This is going to be 0 when R equals 0. That is the origin. That's not the most probable radius. This is going to be 0 when R equals infinity. That is at infinity, which is not what I'm looking for. So I'm looking for this term here. When that term equals 0, I find the most probable radius. And that's easy. That happens for R equals A. Okay, so whenever R equals A, I have the most probable radius. This is called the Bohr radius, and this is, of course, the answer that we have computed before in class. And you know, the answer is still the same. Okay, so that's the answer to question A. So what did you have to do? Several things, right? First, you have to find the right function from the table, clean it up a little bit, then square it, then take the derivative. Of course, don't forget to take the product rule here, and then set this whole thing to 0, finding your answer, in this case, R equals A. Those were the steps that we pursued here. Okay, B now. We apply a photon with a certain wavelength, 121 nanometers, and it's fully absorbed by the hydrogen atom. It leaves the atom in an excited state. Which state is this? in the absence of spin-orbit coupling. Okay, so what do I have to do? Well, first, I'd like to know what is the energy of this photon, because I need to know the energy. So I have to translate the wavelength into an energy, and I can calculate that by taking the expression, which is hc over lambda. Okay, h is the constant of Planck, c is the speed of light, and lambda is given right here. So I can fill it out, and what I'm getting is 1.64 times 10 to the minus 18 joule. That sounds like a number that I believe. Again, every time I get a number out, I just want to check if this number makes any sense at all. 10 to the minus 18 joules are typical energies for transitions and hydrogen and other atoms. So this, I believe, and I can move on to the next part of my calculation, which is now equating this energy, this photon energy, to the energy difference between two states. Okay? How do I do that? Well, I have the energy difference between two states in hydrogen is H times C times R. R is the Rydberg constant. And then if I start from the ground state, what I have is the final state is n squared minus the initial state, which is n equals 1. So this is my expression that I have to solve. I know what H is, I know what C is, I know what R is, okay? And this energy difference then must equal the energy of the photon, which I just computed. Okay, so that's it. I know everything except for this little guy here, n squared, and that is exactly what I need because that gives me the principal quantum number of the state, of the final state. Okay, so that's the answer of my question. So I just have to reorder this, isolate n squared, and if we do that, we don't have to do it every step. Then we find n equals 2. Okay, so n equals 2 will give me this answer right here, and that means that the electron has been excited from the ground state, which is n equals 1, to the excited state n equals 2. It went from a 1s orbital to a 2p orbital. I know that. This must be a 2p. It must be a 2p because delta L must be plus or minus 1. If you start from an s state, which is L equals 0, you must be ending up in L equals 1, which is going to be the 2p state. So the 2p state is the excited state here. So that's the answer to question B. All right, let's go to C now. What is the new most probable radius of the electron? All right, well, the electron now is in 2p. I just determined that. And I'm going to find now from the table the wave function 2p and do basically the exact same calculation as I did in question A. Same thing, just have to do it again. All right, so here's the table again. I have to now to find here n is 2 and L equals 1. So this guy here is the radial wave function that I have to look at. So it's R2, 1, function of R. So let's write that in the same way as we did before, just filling out the value for rho, just to clean it up a little bit. 1 over, oops, this is A, 3 over 2. And then rho here, let me just do it correctly. Don't make any mistakes here. So that is going to be R over A. That's rho. Why? Because I have 2 here, Z is 1, N equals 2. So what I end up with is 1 over A times R. That's this term right here that comes from this rho right there. And then I have minus rho divided by 2. Okay, so I have N equals 2. So this is divided out already. Then I have 1 over A times R divided by 2. So what I'm finding is minus R and then divided by 2A. Okay, so that is the function. And then I have to determine PR, which is the radial distribution function, which is R squared times the square of this wave function. this one. So square the whole thing. That's 1 over 24. And then what I'm going to do is actually I'm going to put this term here, this 1 over a, into this particular square root expression. Okay, so this is not really a square root. This is root 3 over 2. And this is basically 1 over a. So if I combine this, it's going to be root 5 over 2. Square that, that means I get the following. Okay, so it's the square of that expression, root 5 over 2, would be 5th order 1 over a. Okay, and then I get r squared times r squared is going to be r to the 4th. And then the exponential term, square this guy. That means that is factor 2 is going to disappear. And this is what I'm getting. This is what I'm getting after determining the radial distribution function. Okay, so then the final step is to determine the derivative of this function. And again, you use the product rule. Okay, so use the product rule. I have two functions, r to the 4th, and then this exponent. It's exactly the same as we did before. I get slightly different values because this r to the 4 is different. And this argument of the exponential is different as well. But the procedure is exactly the same. So we can just write up what it is. I find a bunch of prefactors, 1 over a times the power to the power 5. And then I can take the factor r to the 3 out and then collect terms. After I take the product rule, I find the following term. So this one here follows from the first product rule, first part of the product rule, which is 4 times r squared times the complex exponent, not complex, times the exponent. And then this is the second part, okay? And I've taken r to the power 3 out so that I can collect terms here, because this here between parentheses is going to give me, again, my root, my correct root, because r to the 3rd is going to be r equals 0. This exponent is going to give me a root at infinity. And so the only root of interest here is this one when r equals 4a. Okay, so that is the answer to this question. If r equals 4a, then I have a most probable radius. That's the most probable radius in the excited state for this electron. Okay, so that was the answer to question C. Then D, take spin-orbit coupling into consideration and then give the term symbols for the level to which we just excited the atom. Okay, so we have to take it into consideration that there's spin-orbit coupling. That's one. And then, of course, we have to know where the electron sits. The electron sits in the 2p state. That's what we just determined. Let's write it down one more time. It sits in a 2p state. And there's spin-orbit coupling in a 2p state. We only have one electron once again. So L equals 1 and S equals half, therefore. And in that case, again, actually, this is kind of getting a little bit repetitive because I have simply P and then a 2 here and then 3 over 2. And the other term was this one. Okay, so that's the same. So single electron in a 2p state always has these two term symbols. L equals 1, that gives you the P symbol. Multiplicity is 2 times half plus 1, that's going to be 2. And then the two J values is 1 plus half and 1 minus half. 3 over 2 and 1/2 is what I find. Okay, so these are the two term symbols. That is the answer to question D. All right, question E then. What is the energy separation between these levels after splitting by spin-orbit coupling? Okay, so what is basically the energy difference between these two states? Now, in order to figure that out, we need an expression, and that expression is actually from the table. Again, there's a list that's provided with common formulas and expressions, and this is one of them. So I don't have to memorize this or write it down. It's on the exam, and this is the energy that I'm after. The spin orbit coupling energy is given by this expression. And what I have to do is to calculate this for both levels and then subtract the two. Okay, so I can do that. Delta ESO. I can actually simplify this a little bit because it turns out that since L and S are going to be the same for both states, both have L equals 1 and S equals half. So if I subtract one state from another state, these two terms will be the same for both. That means they will not contribute. But what does change is the J level. The J level changes. And so I have to consider the J level 3/2 and subtract that from J level 1/2. That is what I have to do. So if I do that, then I get the following answer, H times C times this tilde thing. Okay, and then I subtract from that. So let's just write out this whole thing. Why not? So this is 3/2, 3/2 plus 1. And then subtract from it the value from the second state, which is J equals half. So this one here is going to give me, in the end, the following expression, H times C, A tilde, and then I have half minus 1. That equals 3/2 H times C, A tilde. And that is the final answer. Okay, so 3/2 H times C, A tilde. Filling out these values should give me that answer. So you can actually fill out the number because A tilde is something we looked at in class. And this is not something you have to do on an exam, but just for general interest, this answer is going to be minus 24 joule, which is a very small number. And that's exactly what we found in class because spin-orbit coupling for hydrogen is very tiny compared to the energy differences between the states, between the orbital states. So it's a very small effect for hydrogen. Okay, I'm not sure we can get through problem 8 entirely, but let me make a start with this. This is about the helium atom, and it has 2 electrons. Helium has 2 electrons, and in this case, we're going to consider the ground state wave function of helium. And what I have to do is I have to write down the expression for this ground state wave function. Okay, so in terms of the orbital states and in terms of the spin states. So let's do that. So the total wave function has 2 particles in it, 1 and 2 electrons. And it has a orbital state. The orbital state is 1s. The first electron is in a 1s. The second electron is also in the 1s. Okay, so that means that I have a symmetric orbital state because these 2 guys are the same. And that means I have an antisymmetric spin state, which is going to be alpha 1, beta 2, minus alpha 2, beta 1. That was the antisymmetric spin state. And together, the whole wave function is going to be antisymmetric. Okay, so this is the answer to question A. Question B then. We're going to excite one of the electrons to the 2p state, and then we have this configuration. One electron remains in the 1s, the second one is in a 2p state, and I have to give expressions for the singlet and triplet wave functions that are allowed. So the question is, write down all the singlet and triplet wave functions that are allowed for this configuration. Okay, so I'm going to start with the singlet wave function, which has, what I know about the singlet is that the spin state is going to be antisymmetric, right? Spin state is going to be antisymmetric. That means that the orbital state must be symmetric. The orbital state must be symmetric. And since I have two different orbitals that partake, namely a 1s and a 2p, I have to find the symmetric combination of these two. So what I'm having here is 1s, 1, and then the second one must be in the 2p. So that's one combination. And the other combination is when the second electron sits in the 1s and the first electron sits in the 2p. Okay, so this is the symmetric orbital state for an electron in the 1s and an electron in the 2p. And then I multiply that by the antisymmetric spin state. And that is the same spin state we had above. That has not changed. Minus alpha 2 beta 1. Okay, so that is the singlet state. And now the triplet state. How many triplet states do we have? We should find 3. Okay, and in this case, for a triplet state, I know that my spin state is symmetric because there's 3 symmetric spin states. That means I find 3 triplet states in total. Now, if my spin state is symmetric for the triplet, let's write this down. This is singlet, singlet, and this is triplet. Okay, here it is. Then, if my spin state is symmetric, then my orbital state must be antisymmetric. Okay, so what I can write down then is 1s, first particle goes in there, second particle goes in the 2p, and the combination that is antisymmetric must have a negative sign. Okay, and then the 1s, particle 2, and the 2p now has particle 1 in it. So this is the antisymmetric orbital state. I have to multiply that with one of these spin states that is symmetric. One of them is alpha 1 beta. Gee, this is the longer I'm writing on a single slide, the worse it's getting. Let me write this like this. I apologize. I can barely read my own handwriting here. Alpha 1, alpha 2. This is the first symmetric spin state. Okay, so that's the first triplet state. What is the second triplet state? Second triplet state is exactly the same, got a line here, orbital state, but has a different spin state, namely beta 1, beta 2. Okay, so that is another one. And then the last one, exactly the same orbital state, but has a different spin state. The last symmetric spin state is going to be this combination where alpha 1, beta 2, and then plus alpha 2 and beta 1. Okay, so that's the last symmetric spin state. So I have 1, 2, 3 triplet states and 1 singlet state that comes out. Okay, and these dotted lines here means that I'm repeating the exact same expression here for the antisymmetric orbital state. This one has a half in front of it, and this one has a 1 over square root of 2 in front of it. Okay, hopefully this makes sense, folks. I'm going to stop here, and the last 2 questions of problem 8 will be discussed on Friday, along with the remaining problems on the extra problem set. Problem 9 and problem 10 we will do on Friday. Okay, so hopefully see you then.